Ladies and gentlemen, welcome to this session, which is PID control tuning using Ziegler and Nichols method with Simulink. We have discussed this in class. I won't go much into details. I'll go just quickly so that we'll focus just on our Matlab modeling. These are the rules regarding our Ziegler and Nichols PID control tuning rules suggest an experimental method for determining the PID controller parameters because we need to determine the parameters, especially when we have a plant where we don't know um, the plant parameters. So for us is to uh, do this experiment method to determine these parameters, as we know that a PID you have your P, your I, and a D. Then these are the two scenarios or method that we will look into, whereby one is based on an experimental result of the step response of the plant. Number two, it's based on a purely proportional controller gain value that yields marginal stable system. These are two methods that we use to design a PID controller using Ziegler-Nichols tuning rules. Both methods are based on a transient response characteristics of the given plant. A step response with 25% maximum percentage overshoot can be achieved. Here we'll be looking, this will be our 25%. Then this is the first method whereby you get your S shape has two important characteristics, which is your L and T. Your L is your delay time, your T is your time constant. So once you have this response, then you draw a line tangent, then you can determine your L and you can determine your T. Again, important, this is the table that we use to determine the parameters of PID. So if you are using a PID controller, we are going to use this block here, whereby you'll have the value of T from our graph. We have the value of L from our graph. Then you multiply by 1.2, and then you get your KP. Let us move to the method that we are going to use more, which is second method. Again, what we need here in second method, the second method is used and applicable only in a case where a purely proportional gain controller can bring about oscillatory steps response, not possible for this for the first case or for the first method. With Ti, which is equal to infinity, and Td equals to 0, Kp is increased from 0 to some critical value. Your critical value will be the value, if you keep on adjusting your Kp, that will now give us a sustained oscillation. From a sustained oscillation, as you can see here, what do we get? We get a critical a period, which is your PCR. We get a critical period. So we keep on adjusting our gain. That value becomes your KCR. Then we are able, using the ruler in our scope, we are able to get these parameters, your PCR. Using the experimenter to obtain critical gain and period of oscillations, the controller parameters can be chosen as suggested in the following table. Again, here we have a table for second method. This table will assist us to get your KP, your TI, and your TD. A typical example, we have our value here of our PCR or our critical period. Then you multiply it. If you want to get KP, you multiply by 0.6 because our controller is PID. Then 0.6 times whatever value, and then you have for KP, your TI 0.5 times this value, you get your TI, your TD 0.125 times this value, then you get your TD. So this is how we are going to use. We have discussed this. I won't go into details, but I would just want now just to um, uh, pass this so that when we go to Matlab, we'll follow each other. Now, this is the question that we had in class. It says design a PDI controller for a system shown in the block diagram below using the Ziegler Nichols tuning rules. If a maximum overshoot is excessive 40% or more, fine-tune the parameters to achieve a maximum overshoot of approximately 25%. This is what the question wants us to do, to design um, a PID controller that will be able to achieve approximately 25% of overshoot, as we saw on the graph before, that we can achieve 25% for both method, but we are going to use in this case our second method as we done in class. Now this is the example. The first thing that we need to do here in this example, we must determine our transfer function and or simplify this transfer function. If we have simplified here, where we have s squared plus 6, sorry, s cubed plus 6x squared plus 5x. Then we need to determine, we need to write this on our Simulink. And then again, we already discussed this in class. We know what is our critical gain, but let us do it step by step. Let us go to Matlab. Let us go to Matlab. For time, I will delete this just so that you'll show. I'll see you, and we know we have done this. And I'll remove this and put the gain here. I'll go. We need gain. We need gain. Let's put gain. Let's see. Let's do this. Then we've connected now. So that we have names here. So be clear with you. Have names. Now, as I've said here, I would like to have two input here for our scope so that I can compare with my step input with my output. So this is exactly the same as we have here, this value. Then we said here, remember it says we must keep on adjusting our gain up until we get sustained oscillations. But to save time, we already did this. We won't keep on doing it. But one thing also, um, just as a bonus for you, um, to work smart, you can double click and write dashboard scope. What is this for? It will assist us to analyze our system, or our, sorry, to analyze to analyze our system better instead of keep on moving from one from here to scope. We can have everything here. Sorry for that. Then you can click here to connect with this line transfer function, and we connect with this line step response, which is our input. Then we have now connected this. Then let us go back. Now we said our okay, you can also double click here to change the parameters. You can come here and make our transfer function to be red, set okay, then make our to be green or dark blue, then apply okay. Then we said we will keep on adjusting our gain up until we have sustained oscillation, but because of we have done this, we know is steady. Then steady, and then you can now run. You can run. Let's say double click. You keep on adjusting, but let us stick to 30. Sorry, let us stick to 30 just for I'm showing you what we've already done. I don't want to. Then we can go to a scope. Then we see you have the sustained oscillation. Then you take a ruler. We want our critical period. Then it's 2.793. Then you come here, you put it. This is 2.793. Then you use the table. We have our KCR, which is 30, multiplied by 0.6. This is from the table. Our KP is 8. Then we have our TI 1.3. We have our TD 0.349. Then we can use the values until you have to use the Ki to calculate Ki. This is the equation Kp over Ti. We get our Ki to get Kd. It's Kp times Td. We get this value. Now, therefore, these are all our values that we need to put in our PID. Then we go back to our controller. We delete this. We put our PID. Our PID. Then we open our PID. Then we check the parameters we put here. Then we have KP 18, I 12.885. Sorry, 12.885. Our D is 6.282. We don't change any parameters here. We in the last session that we have in the lab, there was some change these parameters. Please make it a point that it remain parallel, because our focus it's only here for now, our P, I, and D. Okay, then we need to run our, as you can see now, this is our response, and you can see our transfer function or our system, how it's performing. So now our main aim is to have this overshoot being 25%, approximately 25%. Now to check that, because the question says we must tune this PID controller. Now to tune it, it's either you keep on changing parameters here to keep on adjusting, but Matlab also as have an option for us to auto tune this, and it will be able to assist us in getting the required result. The question, it says we have more than 40% overshoot. We must fine tune it to get at least 25%. So that is the main goal. Then we have opened this. As we can see here, this is our current response. Our current response, the dotted one. Then the solid one is the tune response, and we can see the overshoot has reduced, and our system, the state error, and the time is taken to reduce the state error it's quicker, and no undesirable overshoot. But we have not answered the question that we must reduce this to be at least 25%. Let us check here. Again, you can see this is our response, as we can see from our auto tune or our tuner. Now you click here to show parameters. Now you have your parameters here. Let me do this. Now these are the parameters we have here. It's your PID and N. These, when they say block, is the one that is in our design. We have our P18I 12.886, D 6.282, then our N, which is 100. But the tune one, to get this response, we have 10, 1, 9, 202. So these are the parameters the tune suggests. If you want to have this response, you must change the parameters to be like this. Now let's come to the performance and robust. Now the question says our network or our system is 40% and above on overshoot, which is that case, which is 62.8. And our responsibility is to reduce this to at least 25%. Now we have to fine tune this so that we'll get what is expected. Now here, these are the tools that we are tuning tools that we are going to use to get the desired outcome. According to this, we have reduced it to 9.7, our peak is 1.2, and our gain margin, etc. But for us now, we want to have at least 25 here. Then here you have your time or your response time. You adjust this, you make it faster. You adjust your transient behavior, you make it more aggressive, or you make it more robust. So now for us to get at least or approximately 25% here, we can adjust this to, you can just keep on adjusting up until you get the desired output. It's better than keeping on changing a value and here it shows you each and every value that we have. Let us adjust here and see if you get 25, get 17, adjust, get 20, adjust, 22, adjust, 23, 24.7. You can keep on adjusting up until you get 25%, but it's approximately 25%. So we have achieved um, the question or what was required from us, which is 25, um, approximately 25%, which we have here. This is how we are going to use Matlab to design PID. And now after this tuning, because you need to write a report and show the final result after you have fine-tuned your network or your system. You come here, you click update the block. So what this does is taking these values, what we have as our input, as we have fine-tuned our system, take this block and these values and put it here. As you can see now, 10.4 something, it's here. 1.53, it's here. 8.076, it's here. Our end. So this, when you press update block, it automatically put values here on your PID. And then we can go to our network and run our network. The result is, as you can see, this is our results now. This now it's approximately 25%. Or you can also go to the remove the ruler. As you can see, you see now it's almost the same. Now this will be approximately 25%. That is what our aim that we wanted to achieve. Um, then you can then write a report, show all the steps as we will share, if not shared, your your tutorial, if not your tutorial, your practical assignment that will given. I think you'll have one or two questions that we have required to design a PDI controller using Ziegler Nichols method. So this is how you can do it. Just quickly, we had our gain, which was 30, which is our KC, our critical gain. Then with our critical gain, we are able to get to find our KP, we times by 0.6, which was 18. Our PCR, which is our critical period, we get it when you have sustained oscillations. And then to get our TI, we multiply with the critical period, which is 2.793 times 0.5, we get TI. You get your TD, we also multiply with the critical gain. Now to get your KI, this is the equation. This is our KI. To get your KD, this is the equation. We find our KD. Then we plotted this into our Matlab. Then this was our firstly, this was the first step where you get it, the critical period here, which was 2.793. Then after putting the parameters we calculated, this is the response that we have. And then the question was for us to fine tune. Here was trying to keep on fine tuning using manually. And then we have to fine tune using a auto tuner or a tuning block. Then as I tune it, it had 9.7%. Mine was 41%, which is 40 and above, and we have to reduce it to 25%. Then I adjusted my tuning tools, which gave me 25.5% from 40%, and these were parameters for P, I, D, and N. Then I updated my blog. Then this is the result I got. So you can also, when you are doing your report, you can take all these steps and make it when you are doing a report, when you have this figure, about this figure, you must explain which stage is this, so that in your report you will be able to also understand. Although when you are doing evaluation, you'll explain it on your evaluation, but your report also must speak for itself. So I hope this will help you to understand better what is required from you in doing this exercise. Thank you for your time. This video will be will be available on Blackboard anytime. You can go and revisit it and look at it and analyze it. You can go step by step, pause it, and if you have questions about it, feel free to engage with me in class. um, after we've presented the business of the day, I'll have a window or after the class to discuss with these issues where there are gray areas that we need to address. Take care. Bye bye.